Thank you. Thank you very much. Thank you guys for attending this talk. My name is Melchior and I work at Swisscom. I work in the context of monitoring. We are building a monitoring platform. And I chose a small portion of this platform to demonstrate to you, to explain to you. The topic is called automated root cause analysis. So let's jump right straight into it. Let's assume you have a customer, some external customer, going to the Swisscom shop. He wants to buy a new mobile subscription, for example. By the way, who here is a Swisscom customer? Relatively nice. Okay. All right. Don't worry, I'm not here to make you switch providers, so that's fine. All right, so let's assume the customer makes a request to some website, or all right, he wants to order something, and of course, this system, let's assume it's some REST API is going to trigger some other call in some other system, right? And then this other system is in turn going to trigger some other call somewhere. And there is a chain of interaction until the customer's request is fulfilled. So for example, he orders a router at home and the post order is created. Or for example, he wants to block his SIM card and the SIM card is actually blocked. You know, you have a set of steps. And we have a clear start and a clear end between the customer triggering the action and when the action is actually performed. And this whole chain is called the top business process. And the top business process is really something that Swisscom wants to monitor heavily. This is the critical part of Swisscom that needs to be taken care of. And the challenge of this top business process is that it's actually split into different zones that we call resources. A resource in the Swisscom context is actually an application. You can think of it as an application. Let's say a team is managing its own application. It has a set of microservices and they care about their own context. You know, they care about their monitoring of their application, but the top business process is actually going through a set of these resources, and none of these engineers, these teams, is actually the owner of the top business process. That makes it hard when you have something going wrong in the chain, because the full chain is actually affected, the top business process is affected, but how are you going to take care of, like detecting first that there is a problem, then finding where is the root cause, making everybody collaborate into the investigation? This is a very hard problem at the Swisscom scale. Because just to give you some other idea, some of these top business processes, each customer action triggers 40 to 50 different microservices spread across 8, 10 different resources maybe. So it can be quite big. So in this context, a few years ago, Swisscom created Mosaic. So Mosaic is the name of our platform. And our mission is to provide the end-to-end transparency on Swisscom's most important services and processes. That's the goal. And there are many things in our platform, and I'm going to focus on one specific area. And for this area in particular, well, the thing that we are sourcing to do that, to monitor this, is based on distributed tracing. So I guess you guys know the concept of distributed tracing. And the idea here is that we're going to enforce everyone kind of to have the same way to do distributed tracing. In the ideal case, we have now the normal stack is Tempo. So every team at Swisscom is supposed to have, let's say, send their spans and traces to Tempo. Unfortunately, it's not always as nice. In most cases, fine. You have a set of Spring Boot microservices that you can easily instrument with some hotel collector. In some other cases, it's legacy applications where, they cannot really easily instrument, and it's quite hard. But let's say ultimately what we do there, to sum up, we source everything into Kafka and goes into our platform. Once it's there, we're going to do end-to-end correlation so that we can have end-to-end traces across the company. We're going to do enrichment. We're going to do TBP, this top business process identification, right? And we end up with spans and traces nicely correlated. And out of this, we're going to try to monitor different things. So the first thing we're going to do is we're going to build metrics per function. When I say function, it's the abstraction between a microservice A calling a microservice B. You have a set of spans. All of these spans, they make some abstract entity called the function. And for this function in particular, we measure three things: number of calls, number of times that these calls resulted in some error, and the P95 duration. So 3 different time series per function. Now, once we have all of these time series, we're going to want to monitor them. How do we monitor these behaviors for each of these functions? Well, we're going to dump everything somewhere, and it's going to stay there. And there is a retention currently of about 2 months. And we're going to have a machine learning model running on a schedule every day. He's going to learn these 2 months of data, he's going to learn seasonality, trends, patterns on every of those time series, and he's going to make a forecast. He's going to make a prediction over the next 24 hours for each of those time series. And with the forecasting, well, very easy then to do anomaly detection. So the idea is that we compare the observation on the reality with the prediction of the machine learning model. Whenever the observation lies within the bounds of the model, it's fine. Whenever the observation is outside of the bounds, that's an unusual event. It's an anomaly. So again, the anomaly doesn't mean that something went wrong, just means something unusual, unexpected happened. So that's how we go from distributed tracing to anomaly detection. And once we have these anomalies, well, we cannot stop there. The anomaly can mean many things. So we're going to have an aggregation called the health score. So because you have different types, we have the traffic anomalies, the error anomalies, the duration anomalies, and we have a certain amount of anomalies. We have a severity, the height, the spike, many different things. And the idea is that we have a way of combining this into a health score. So we have a definition. Let's say every single function at Swisscom, so each function can be just some endpoint on some REST API, has a health score between 0 and 100% with some definition of what it means. And the idea is that we're going to propagate this health score. So this is let's say, a smaller version of our domain model. There are the entities, but just to explain to you the ones that we're going to talk about, we have the function, right? And this function belongs to what we call component in our context. Component can be any microservice, database, API, right? And this component belongs to a resource. So the resource is the application managed by a team. They have a set of components. These components call each other with functions. And optionally, these components, they can impact a top business process. And now that we have this domain model, we're going to have health degradation. So we have seen we can aggregate the anomalies into a function health score. And once we have a function health score for each of the functions and component, we're going to have a way to propagate, let's say, the health score, the degradation. So we're going to have a way to compute the impact. Not every function is as relevant as each other for the component. But let's say, skipping a few details here, we have at some point a component health score that is an aggregation of the function's health score. So each microservice now has a health score coming from the anomalies of its functions. And this health score is further propagated to the resource and the TBP level. And now, with all of this, we went from distributed tracing to a health score on the top business process level. And this health score, of course, you can do alerting, etc. So that's already quite nice. And what's nice about doing this bottom-up, because I've seen in other contexts, monitoring context, trying to go top-down. If you go top-down, like you try to say, I'm going to detect if something's wrong with my top business process or some high-level entity. And then what? Once you're there, you want to know what went wrong and you have to drill down. How do you drill down? It can be quite hard. With this approach, which is bottom-up, you get this for free, basically, because the degradation that is at the top is coming from the anomalies coming directly from the spans. And the second part goes into, we're talking here about the detection part, right? And there is actually the next part, which is the resolution. So if we look now a bit at the life cycle of an incident, let's say of an incident at Swisscom, so something major is happening in Switzerland in some segment, well, first problem occurs, right? Then at some point, hopefully, the issue is detected by the service control center. And then they're going to start the collaboration, the investigation, triggering many teams, and they're going to start investigating what is wrong. And at some point, they're going to figure out what is the root cause. And once they figure out the root cause, they're going to start to repair it. So the first part, as you probably guys know, the first part is called MTTD, the mean time to detect, so the time it takes to detect an issue, and the next part is called MTTR, mean time to repair. And the MTTD was quite high when we started, like some cases could be like 10, 15 minutes, and now with our platform, which is a near real-time pipeline, we have a detection with anomaly detection in 30 seconds, 1 minute, so this is no longer an issue. But the MTTR was still quite high, and the biggest part is actually this root cause analysis step. The resolution is fine compared to this RCA part, right? Because usually, like some network engineer did the wrong IP tables configuration, fine, we just revert it. Somebody make a deployment, made a commit, fine, just revert that commit. The hard part is to find what went wrong exactly and what needs to be done. So the root cause analysis is the part, the focus here I want to talk to you about. So first, some definitions, because in the context of RCA, we have always very, even inside Swisscom, different meanings for RCA. And this is my personal way I think about it. Root cause analysis is the human process of finding the root cause of an issue. And what I call auto-RCA, or automated root cause analysis, which is the title of this talk, is the automated process of creating causal graphs and computing the most probable root cause. Causal graphs is key here, because when you say root cause analysis, there is like finding a cause in something. If you have only one information that is one signal that is wrong, there is no root cause to analyze. That's the thing that's wrong. To talk about root cause analysis, we need at least two things that went wrong and a causal link between those two things. Otherwise, there is nothing to do in root cause analysis. So the idea is to figure out the different signals that are wrong and what is linking them, basically. So to do this, we need three categories of information, roughly a very large overview of what we do for this auto-RCA. We need first the monitoring information that I just explained, so the anomaly detection part. And then the second part, which is events enrichment, so we can correlate with different events happening externally. And the third part are the dependencies. We need to have strict dependencies between those things and know how they relate. Once you have all of this, you can create a context, you can create an RCA issue. The RCA issue has its life cycle, a start and end. We can alert based on that. The advantage here is that an RCA issue will have everything in the context with one ID. It can be tracked. It can be a reference for people to collaborate on. It's not like n problems now spread across different teams. It's one single problem managed by the service control center that includes everyone. So as an example, it can be the first part for the detection can be we have some anomalies, right? And some components are degraded, some TBP is affected. The event enrichment could be, for example, that component 2 was deployed. And the last part about the dependencies could be, for example, that C2 is impacting C1 and C1 impacting C3, these kind of things. And once you have all of this, basically you can create a causal graph. So roughly in our UI, it matches this picture here, where you have on the left side a deployment. This deployment triggered, in this case, duration anomalies, and this affected the health score of function 1, which affected the health score of component 1, and component 1 is actually a cause of component 2. This we figure out using distributed tracing, right? And component 1 and 2, they both affect resource 1 and the top business process 1. So this graph, it appears as a single view on our UI. Of course, every node is clickable. You can give feedback and these kind of things. But the idea here is that everybody involved in the issue can see this graph and immediately you see, okay, from deployment to top business process, we have the full chain. And immediately you can see if you have an impact somewhere at Swisscom, what exactly caused the change. So this is how we speed up the RCA part. This is how the automated RCA is basically helping the analysis. Now, I wish that the graphs were always looking this nice, like you have a single deployment, single TBP, and fine. It's not always the case. Many data quality reasons, the bad instrumentation from different teams, bad deployment names, and many different things. And it's not always the case that you can identify as easily a single root cause. In many cases, you have many different root causes, because if you look at a graph, what is a root cause in a causal graph? Well, it's basically a node that has 0 in degree. That's it. But sometimes you have several of them. So what can you do then? Well, the general idea that we went through is to say, if we want to go further than that, usually if you look at an issue and want to estimate a root cause, you need to look at the past. You need to look at similar issues that occurred in the past. That's the assumption, let's say, that what the past is what is relevant for the current investigation, because many of these issues are repeating offenders, maybe not always having the same impact, but we can learn a lot from the past. So to do this, we need to have a notion of graph similarity. If you look at these two graphs, could think like, how are these two graphs similar? Like we see F1, function 1 is both degraded in both cases due to duration anomalies, not exactly the same amount. Function 2 and 3 are not present only in one of those two graphs, and the components are different. Component 2 is present in both, but doesn't have the same health score. All right, how are these two graphs similar? Can we compute it? Basically, it boils down to having a mathematical definition of the similarity. You have two issues, they're both defined as graphs, a set of vertices and edges, and you need to find a similarity function that's always between 0 and 1. Not going to share here all the details about this. You can do this with graph embeddings and this kind of things. We didn't need to go into something that complex that requires training. We could directly do it using our topology to have basically a weighted sum of different attributes and then pass it to some sigmoid activation function. And then we had a nice similarity function between any two graphs in the pipeline. And this allowed us to create a similarity module. You pass some RC issue, it gives you back the top X similar issues with scores above Y. This is a nice building block because then once you have this, you can leverage this for different use cases. And the first one is the probability estimation. Once you have this, it's fairly easy. The idea is this: if you have an issue occurs at some point, and you have two root causes, well, let's imagine it's the first issue like ever. You have nothing to rely on. Well, it's 50-50 probability. And then a second issue occurs a bit later, and you look at the similarity. And let's assume that based on the similarity function, they are considered highly similar. Then you're going to look at the root causes in the second graph and say, did it occur in the past? How often was it a root cause? And you see that the first one, we already had duration anomalies on function 1, and the F3 function was not seen before. So maybe we can have a different probability distribution. Here it's a slight effect, but it gives investigation a sense of priority leveraging the past. And this can be even higher, this distribution, using feedback. So imagine that the same scenario, 50-50, and then investigation comes in, user is giving feedback and saying, I have the business context based on post-mortem analysis, and I can tell you the first one is really the root cause for sure. So now the probability is 100%, 0%. This means that in the second case, when it comes in, we can leverage this information, maybe have a bit of a higher probability distribution difference. These numbers are just the idea. It's not exactly how our algorithm is working, just to give you the gist of the idea. So with this probability distribution, we can give a hint to the investigator what is more likely. We can also give them links to the similar issues in the past, etc. And this is all in the goal of helping speed up the RCA. It's not automating a solve, right? It's just giving a hint to the investigator of the service control center who is working on the issue. Now, that's already nice. And we're thinking like, what is missing? Where can we go further? How are they working? Once they start to work on an issue, this issue is linked to a lot of tickets. They create tickets, they create incidents in other platforms. Swisscom has a lot of different ways of handling this, depending on departments. They do post-mortem analysis. So at some point, investigators are going to write comments about issues and say how they solved it. And we were wondering, like, can we leverage this? Can we use this, especially since these comments contain information that is normally not present in the graph? Because not everything is sourced. Usually, like, the real root cause maybe lies behind the graph, and we don't really see it because it's not part of distributed tracing data we source, not part of any correlation. And if we're reasonable and say we cannot expect this to be part of the structured data that we source or correlate in any way, it's always going to be in comments. Well, we have to rely on an LLM. LLM can help here and interpret those comments. Many ways to do this. Like if you say, let's leverage the similar issues in the past and what people said about them, we could say, okay, let's train something. We didn't need to train anything. We can just use RAG. So the RAG, just as a reminder, it's quite kind of a hack. Like you give a prompt and you're like, okay, let's do some vector embeddings. Let's compare in the vector database, retrieve, and you pass the full context to your LLM. And kind of a hack because the user is under the impression that the LLM is going to give you the answer where actually the full answer was already in the question, but that's just thanks to the enrichment of the context. And in our case, what we could do is kind of something similar, but even simpler because we didn't need vector similarities using those algorithms from vector database. We could just pass an RC issue, call our similarity module, and pass the full RC issue as text. Quite easy to convert this to text and pass all the similar issues. And this is given to the LLM with some prompt to say, what is the most probable root cause? What is the problem here? Can you help us the investigation? Doing some further help on that. All right, let's try to make a short demo. So here you have an example of one of those issues. So you can see, for example, that you have some duration anomaly, some unusual error. It triggered some errors on some function, on some component. We have some deployments that here are found on this resource. It affected some top business processes. And we have now some AI summary here. And the AI summary can basically tell you, well, it's a cascading effect. It can explain to you a bit what you see in the graph and say, this is actually something that we have seen in historical patterns. And here are the past similar issues where we have seen this kind of stuff before. So it's nice. It's not really the why we built the LLM. It's already nice because it serves kind of an educational purposes. Some of the investigators are not so familiar with the tool. Maybe the graph is a bit intimidating and they rely on the assistants a bit to help, but it's not providing any new information, even the similar issues, because these similar issues, you can find them and click on them in the UI, you can see them. That's not really the point. But the real power comes when you have feedback. So now I can show you a mock example. It's not a real life example. Here you have an issue that happened in October 2025, and I myself put a confirmation feedback, and in the comments I put, maybe zoom a bit. I put here that the root cause was a MariaDB failure behind proxy writes. This is completely fake. Just assume that you have some MariaDB failing and that we don't see it in the graph because for some reason it's not sourced. And then another issue occurs like in January this year. And I put again a confirmation feedback and I said the root cause is still the same MariaDB failure that we had in October. Now what happens when you have a new issue that comes in a bit later? And this issue is considered similar to the two issues that we had in the past. Now, what is the AI summary going to tell you? It's going to tell you the root cause was a MariaDB failure based on similar issues and secret comments from previous incidents. And while this is a toy example, based on a very simple feedback, it shows, I cannot give you like real life example from production incidents here, but it shows you the power of how we can leverage the past, because now if investigators write comments in anything that cannot be parsed, especially at Swisscom, they write even like full investigations in Swiss German, then of course only the LLM can save us here. Right. Yeah, so that's about it for our demo. And with that, with a little bit of time left, I'm ready to answer any questions you have. Thank you for your attention.